Okay, yep. So you look for something that minimizes the distance that the current will travel through the material and the surface area, right? And we just use, and then in the question, they don't actually they actually calculate the resistances for all three sides, right? And you just use the geometry of the problem, the thickness that it, so for the x in the x direction, just L is equal to 1 centimeter, and the area is just multiplied by the block, right? And as we could see, this is indeed the smallest resistance, offers the smallest resistance. Okay. Any other problem? Another problem you guys want to do? You want to do chapter 24 or anything from chapter 24? Okay, we can go over a few of these. So the energy in the capacitor, how does it change if it's doubled? You just look up the formula that we've derived in the past for the potential energy, right? And this is just 1/2 C V squared, which I think we derived in the class. And we could see that if we double the potential, it increases by 4 times, right? Because it's V squared. So if you know, V2, let me get this. Okay, so we have this, right? And it's V squared, so it quadruples, right? And then for B, what if we change the charge on the, if the plate on the, if the charge is doubled? We can convert the potential energy in terms, and from V to Q using the equation for capacitance, right? We just, C is equal to the charge over V, and we could just plug in V over here for that, plug in Q for V over here, and we get this. So we could also see that it quadruples. Now the last part of the question is, if the plate separation is doubled as the capacitor remains connected to the battery, what would happen in this case? This isn't exactly clear, right? So, well, the potential stays the same, and we have to see how the capacitance is, right? Now, the capacitance for a parallel plate capacitor is just, let me write it down. Right, E times A over D, where D is the plate separation. So now if we look at this equation, if we double the distance, we decrease the capacitance by 2. So that means that the potential energy decreases by 2. So we have the potential energy, right? Now, like physically, think about it, right? We have these two plates that are attracted to each other, right? Because it's one side is positive and negative, and the other side, one side's positive, the other side's negative, right? And we want to pull them apart. Let's say we pull them double the distance, right? we're decreasing the energy in that system, right? Where is that energy going? What's removing that energy by pulling it apart? My hands, right? I'm taking it and I'm physically moving it apart, or whatever you're doing to separate it with, right? I'm doing work on the system, right? And I'm decreasing the energy, right? I'm subtracting energy from the system by actually physically pulling apart because they're attracted to each other. So it's going to take energy, right? No, the charge remains the same, right? We're just pulling it apart. By pulling it apart, there's less field. Think about it. If you think about it, right? The electric field becomes smaller. So, right, there's less attractive force when they're that far apart. Okay, now let's move on. Let me clear all the drawings. Okay. Okay, so let's do let's do 24, right? Suppose we have 3 parallel plate capacitors whose plates have areas 1, 2, and 3, and separation and respective separations. We connect them in parallel, and they ask us to show that this will be the equivalent capacitance of the 3 capacitors in parallel, right? So if they're in parallel, we know that the potential that each capacitor is kept at will be the same, right? So that means that we'll have this, right? Q1 is equal to C1 times V, and the same goes with Q2 and Q3, right? This is the voltage. And then we could plug in our definition for capacitance, right? Capacitance is not determined by how much voltage you have in the system. It's actually determined from the geometry, right? That we calculate based on the configuration of the conductors, right? In this case, for a parallel plate capacitor, it's given by this. We have these 3 equations for the charges. Then we also know that the total charge that's developed is equal to the sum, right? The total charge that we pull from the battery is equal to the sum of the 3 plates in the 3 parallel capacitors, right? Each capacitor is drawing some amount of charge from the battery, and you sum it all up, right? And they're all kept at the same potential. So then we have this equation over here, right? Now we simplify it to this, right? And finally, to calculate the net capacitance of the whole entire system, the three capacitors combined, well, all we have to do is divide the total charge by the voltage. Right. Now, for a particular capacitor, this will never change, right? So we'll find the total charge, which is just given above, and we divide it by V, and we find that the solution is just the sum of all three capacitors. Right? So a lot of these problems, you just take the equation for capacitance, which is C is equal to Q over V, and you manipulate it in a certain way, right? And you also have to know the formula, how to calculate the capacitance for different geometries, right? And know the general rules on how to calculate the capacitance. And then for like a simple capacitance circuit like this, we could calculate the equivalent capacitance of no matter how many capacitors we have, right? And we know, and we use the two rules where if it's in series, well, let's do parallel. For parallel, right, it's just like we calculated up above. Okay. Now I'm starting to get used to writing on here. For series, it is, right, just like resistors in parallel. Right. And this is for three capacitors, but you could extend this for however many you want. All right. Now, and we use these two rules to calculate the capacitance, right? And just like last time, we'll combine it. We'll start with the most complicated part, which is C1 and C2 in series, because that's connected. C1 and C2 in series is connected to R3 in parallel, which both of these are connected to R4 in series. So this is the innermost section. So we combine that first. If you go down, they combine it. It becomes 1/2 C. And then they combine 1, 2, and 3. And since they're in parallel, you just add up the 1, 2, and the 3, and then you get the equivalent capacitance of these three capacitors. And finally, we combine those three, the equivalent capacitance of these three, with the fourth one, which is in series. We add it up accordingly. We do that, which is the same as resistors, just that resistors, what you do for series and parallel are switched, right? For capacitance, you add them up. For series, you add up the reciprocals. So this section is pretty straightforward. So let's work backwards. You want me to do one more problem because of all the time that we missed? You have a problem you want me to walk through? Fair enough. So electric field lines. Why don't we? Okay. So for electric field lines, to draw them, we follow several rules, right? The field lines represent the direction that a positive charge would move in if we just put it on a piece of paper with these two charges, right? And if you look at it, if you look at this, these are two charges of the same sign. And when they repel each other, the lines don't end up touching each other, right? Because for the rules for the electric field lines, it begins on a positive charge and ends on a negative charge. So these lines can never cross, right? Or never connect to each other because they both have to move away from the positive charges. And the same thing is true with the negative charges. We have two negative charges over here. Well, they'll be pointing the opposite way. And if you notice, and now along with here is we have the equal potential lines, right? And if you notice, where there are no lines, no electric field lines, there's no change in the potential. If you look over here, there's no other equal potential lines in the middle, right? It's because there's no electric field lines. It's kept at the constant potential in the middle. And the electric field lines are always perpendicular to the equal potential lines. So think about as these two charges are on a hill, right? The lines themselves, the electric field lines, represent the direction that a ball would roll down the hill, right? And the equal potential lines represent all the areas at the same height. So a ball rolling down so the equal potential lines represent the same height, right? The ball is not going to roll around the mountain at the same height. It's going to roll downward, right? And these are always going to be perpendicular to each other. And this is the general rules to draw electric field lines. Now moving on. So why don't we do one of these problems, actually. They're pretty good. All right, so let's say if we have 2-point charges, right, in a line, the simplest case. We'll finish up with this problem, and we'll go to a two-dimensional problem after this. This is a one-dimensional problem. We have two charges on the same line, and we want to calculate the electric field at different points, or in this case, the electric field and potential. So first, let's find where the electric field is 0. For this, we'll use the equations for the electric field of point charges. So this one is the electric field due to point charge 2, which is right over here, and that has a negative charge, right? And then we sum it up with the electric field of 1, right? The electric field at one point is a superposition or a sum of the electric fields of all the charges in the system, right? So we add up the electric field due to every charge at that particular point, and that's our total electric field. And in this case, that's what we added up. This is the electric field from charge 1 to charge 2, right? And it's asking us where the electric field is 0. So when we start off with this problem, we have to figure out which region the electric field is 0 in, because this will change whether we consider E positive or negative, right? So just from a simple logical deduction, we can figure this out. So charge 2 is negative and charge 1 is positive. So now let's imagine if we put a point charge in different areas. Let's say if we had a point charge over here between the two, right? A positive point charge. It would be attracted to the negative and repelled to the positive. So it's always going to feel a force this way, right? For the electric field to cancel out, we need it to be repelled by the positive charge and attracted by the negative charge in the same direction, right? Well, it's going to we want it to be attracted in one direction and repelled in the other direction, right? And if we look at over here, let's look at on this side first. It's going to be one, in this case, it's going to be repelled from this and attracted from here. So it'll work outside on this side, and it will also work on the outside on this side as well, because here it's going to be attracted to this side, and it's going to be repelled over here. It's going to be repelled from point 1, right? So there's a zero field. There could be a zero field on both sides of this, right? But then we have to look at the magnitude of the charge, right, to see which side it'll be on. Because if the magnitude of the charge is, if the magnitude of, in this case, the positive charge is higher than the negative charge, because if this test charge sits on the right side, this will always have a larger force than this, right? Because this has a higher Q, and it's also sitting closer to the test charge. It's always sitting closer to the test charge. So it can't, the zero field can't be on this side. So it has to be on this side, because this is the smaller charge than this larger one. So all we have to do is bring that point charge closer to this to compensate for the fact that this is a smaller charge. Does everybody see that? So there's 3 regions that we consider where the field could be 0 first. Left, in the middle, and then on the right. And then based on the polarity of the two of the charges and their strengths, we can narrow this down into one location where it's 0. So it's on this side, right? And we set up E accordingly, right? So when it's on this side, the positive test charge would be attracted to the negative charge, to Q2, because it's negative, right? So it's going to want to move in this direction. So it experiences a positive force in this case, because we always consider from left to right to be the positive direction. So this is a positive force. For Q1, we find that the force is negative, just like we decided that this is a good region because it has an opposite force, right? So this would have a force in the negative direction, or the electric field, because we're just talking about positive test charge here. So then we write out the equation for the electric field, or the force on a positive test charge. And if you notice, we put the distance in terms of the variables given to us, right? X is this distance from the positive, from charge 2, and then the distance from charge 1 is D plus X, right? Where D is the distance between these two charges, charge 1 and 2, plus X. We want to find a position where this is 0. So we set this whole thing up to 0, and all we have to do is solve for X. And that's what we do over here. We solve for X, we expand, we use the FOIL to expand, and we find that X is equal to this quantity over here. We find that it's 16 centimeters to the left. So we really set up this problem by using some logic to see what region we expect the test charge to be 0. And in this case, it would be on this side, because on this side, there's a certain distance from these two charges where these forces are equal and opposite. And it doesn't occur in the middle, and it doesn't occur on this side, right? It doesn't occur on this side because of the magnitudes of these two forces, right? And to find out where it's zero, we just set these two electric field components to zero. We set it to zero, and then we find where that distance is. And that's all she wrote for this problem. Now, or there's a part B, where the potential is zero. So where the potential is zero is we do the same method here, right? We get the potential from location 1 and the potential from location 2.